Hi everyone, welcome to this week's session in which I'll be continuing with the theme of regression, which I started to reintroduce in last week's session. So to get us going, I'm going to start by reviewing one of the analyses that we went through last time, a multiple regression analysis. So in this piece of research, the researcher was interested in testing whether organizational identification would predict stronger commitment to an organization, but also when controlling for, adjusting for, or over and above other factors that might predict commitment, such as job satisfaction, salary, age, and sex. So they took a questionnaire, self-report measures of all of the variables, salary assessed as annual salary before tax. And we noted that what the analysis might do, what they're interested in, is whether identification will predict commitment while also taking into account or adjusting for these other things that might also predict commitment. And we noted their analysis option as being multiple regression, which allows them to test the role of individual predictors in explaining variance in commitment, while firstly controlling for the role of other predictors that might do so, and secondly while assessing the overall fit of the model in terms of variance explained, R squared, of the model. Okay, I'm just going to remind you of some key bits of that output. So we highlighted that the model that included all of those predictors explained 46.5% of the variance in commitment, indicated by the adjusted R squared. And that amount is significantly different from zero, as indicated by the ANOVA test here. Then looking at the coefficients table, we noted that identification was indeed still a significant predictor of commitment when adjusting for these other predictors. So these are the coefficients, the t-statistic and the p-value. Of the other predictors in the model, salary and job satisfaction also uniquely predicted commitment positively. So as annual salary and job satisfaction went up, as apparently so did commitment. In contrast, the demographic factors of age and sex did not significantly predict commitment. We also considered the specific meaning of these coefficients and values in a multiple regression analysis. Specifically, that the coefficient and the significance of it indicates whether that predictor explains a unique part of the variance in the outcome variable, commitment in this case. In other words, part of the variance that is distinct from the parts explained by other predictors in the model. And that's estimated when those other predictors are held constant, either at their mean values in the case of continuous predictors or at the reference category level for a categorical predictor like sex. Okay, so that's our takeoff point for today. And what we want to consider now is whether the researcher might want to know something a little bit further than the information that can be gleaned from the previous output. So that's certainly consistent, what we saw, with the hypothesis that identification would predict commitment even when adjusting for or controlling for those other predictors. But our researcher might also be interested in the specific additional contribution of individual predictors. So for example, how much variance in commitment is specifically attributable to identification. So when we're considering a question like this, what's the contribution or the role of an individual predictor or an additional predictor that we add to a model? There are a couple of aspects to this. Firstly, we might consider what the size and significance of the regression coefficient is. Is that coefficient positive or negative, and is it significantly different from zero? Now, we can largely already tell that from the multiple regression analysis we already ran. But we might also be interested in how much they explain, how much they contribute to explaining variance in the outcome variable in terms of the R squared value. And for that, we need to do something a little bit different. We need to run a hierarchical multiple regression, which is essentially running multiple regression but in several steps, at each of which you add an additional predictor or set of predictors to your model. So let's go back to our data set and run that analysis not as a straightforward multiple regression, but as a hierarchical regression in several steps. So let's go to regression, linear regression. Okay, so commitment is our dependent variable. Annual salary, identification, job satisfaction, and age are our covariates, and sex is our factor because it's categorical. Okay, so I'm just going to actually ask for the other things that we want as a sort of almost as a default in our multiple regression analyses. We want the adjusted R-squared, the F-test, the ANOVA test, the confidence intervals for the unstandardized coefficient, and we also want the beta coefficients as well, the standardized coefficients. Now, under this model builder option here, this is where we can specify the blocks or the steps in which we want each of these predictors to be entered. Okay, so in block 1, rather than entering all of these predictors at once, I'm just going to enter identification. I'm just dragging it across here. Now, I also want to specify a second block. This is basically saying, please run a second regression analysis in which, as well as this variable, we add in some additional variables. In this case, I'm just going to choose job satisfaction, age, and sex. Here, I'm going to ask for just their main effect. So I just want to look at the effects of job satisfaction, age, and sex in this second block. And I'm going to add another block, a third block, in which we enter annual salary. I'm just dragging that and dropping that there. Okay, so you may be wondering at this stage why particular predictors are being entered in particular steps. Now, in a sense, the order in which I've done it here is arbitrary. It's just for the purposes of illustration. So there's nothing inherent in these variables that means they have to be entered in block 2 or block 3 or block 1 or whatever it might be. Instead, the order in which you specify these variables to be entered is something that relates much more to the actual research questions that you have, the hypotheses and the information that you want to glean from your output. So that's something that I'll return to in a little while to consider, when and how you specify your hierarchical regression model. So for now, what we have is a hierarchical model, a hierarchical regression analysis, in which we've entered identification first, followed by a block with job satisfaction, age, and sex, and a third block with annual salary. Okay. Now, just before I go back to zoom in on key bits of the output, I want to show you a key thing here in Jamovi, which is now this coefficients table looks pretty much like the multiple regression output that we already had. And in fact, this final model, model 3 as it's called here, is pretty much the same as the multiple regression output that we saw, the model that we saw already. Now, when we've run a hierarchical regression with several different blocks, we get an extra little drop-down option here in Jamovi. So the default is model 3, which is the model that contains all of the predictors, but we can also ask for the coefficients in model 2, which is the model that includes the block 1 and block 2 predictors, so identification plus the other 3 that were entered in block 2. We can also ask for the coefficients for model 1. Now, model 1 just had block 1, so that just contains identification. So we can toggle between the coefficients table for model 1, model 2, or model 3 in our Jamovi output. Okay, let's zoom in on some other key bits of the output. So firstly, here in the model fit table, we have not 1 but 3 sets of R-squared values and the tests of whether they're significantly different from 0. And then we also have a second table here of model comparisons. So I'll start there. Okay, so this first row is giving us a value of the change in R-squared between models 1 and model 1 and model 2. So this little triangle figure here is the Greek letter delta. Okay, so delta indicates change. That means change. So this is the change in R-squared between models 1 and 2. Okay, and it's suggesting that the change in R-squared, which actually, just to say where that comes from, is simply, literally, the difference or the change between the R-squared value here from model 1, which just had identification, and the R-squared from model 2, which had those 3 additional predictors. And that is 0.057. Okay, 0.4 plus 0.057 gives you that. Okay, so that's where that comes from. Now, what this is indicating is that adding those 3 additional variables, job satisfaction, age, and sex, in block 2 explains an additional 5.7% of the variance in commitment. And that additional variance is significantly different from 0. Okay, so another way in which you might hear that expressed is adding those 3 predictors in block 2 significantly improved the model or improved the fit of the model. Likewise, the second row gives us the comparison between model 2, which has identification, job satisfaction, age and sex, and model 3, which then in turn added annual salary in that final block, that final step. That suggests that doing so, adding annual salary explains an additional 3.1% of the variance in commitment. And that again is significantly different from 0. And in turn, up in the set of ANOVA table, the ANOVA results, if you like, it suggests that at each step, the amount of variance explained in commitment was significantly different from 0. Okay, right. So that's our sort of our way around a hierarchical regression output. Now, I just want to go back to that question. That's a very important question of where and how you should specify each predictor to be entered, or set of predictors to be entered in hierarchical regression. And ultimately, again, that is not a question of statistics per se, but a question of theory, hypotheses, of your research question, of what it is precisely that you're interested in knowing from your data. So let's look at how we can frame a given question a little bit differently and see how that shapes how we would specify our hierarchical regression analysis. So let's say in fairly bold terms that our researcher is interested in the effect of one predictor, or whether it predicts an outcome variable, let's say identification predicting commitment, over and above or adjusting for some other predictors. So in one sense, it might be possible just to do that using a straightforward multiple regression in which all of these predictors, X, Y, and Z, are entered in one block. So that would already give us, as we've seen, an overall test of the R-squared and its difference from 0. And it would also give us tests of the unique predictive roles of X, Y, and Z, their coefficients, and whether those are significantly different from 0. Now, our researcher might be interested in something a little bit more subtle. They may be interested, first of all, in whether variable X, let's say identification in our example, whether that in and of itself, by itself, predicts commitment. And then they're interested in whether it stays significant, if it is significant, once we start to add in additional predictors to the model. And that's where a hierarchical regression might become a little bit more useful. So in that case, if that's what they're interested in, the researcher might first specify a model in which they enter variable X first, let's say identification, and then add these other predictors in a second block. Now that in the first model gives them an estimate of the R-squared, the amount of variance explained in commitment, say our outcome variable, by variable X, identification, without those other predictors. And then it also, and a test of whether that's significantly different from 0, but then it also indicates what happens to that variance explained, the effect of X, if you like, when we've added some additional predictors into the model at step 2. Does it stay significant, for example? Does the coefficient decrease or perhaps even increase? Alternatively, our researcher might be interested not just in whether X predicts the outcome variable over and above Y and Z, but they may also be interested in whether X or how much variance in the DV is explained by X in particular. So how much variance in commitment is explained by identification specifically when adjusting for all these other predictors. So in that case, what they might do is instead specify all the other predictors to go in first, or in a series of steps if you like, and then in a final step add in identification. So not entering X or identification in first, but actually entering it last by itself in the final block. And what that will give you is a change in R-squared value for X over and above the other predictors. So how much additional variance in the outcome is explained or attributable to X or identification. and a test of whether that is significantly different from 0. All right. So in that sense, a hierarchical regression analysis, if you're interested in the amount of variance specifically attributable to a variable or set of variables, you can enter that last. But if you're interested in how much they explain by themselves and how that changes when additional predictors are added to the model, then you might enter those variables first and then add in the other predictors. Okay. So that's hierarchical multiple regression in theory. So let's look at how we can re-specify that analysis to see what information it might give us. So let's just go back to our example. Okay, that's the one that we just ran. I'm just going to start from scratch. So again, we have commitment as our DV. We've got our 4 predictors that are covariates, and sex is our factor. Now in this model, rather than identification first, I'm going to specify annual salary first. In the second block, I'm going to also put in job satisfaction, age, and sex. Okay, I just want the main effects for that, so job satisfaction, age, and sex. And now identification is going in the last block. Okay, and I also want the normal things that we ask for in any multiple regression, our f-test, the adjusted r-squared, confidence intervals, and the beta, the standardized coefficient. Okay. So let's look at that output. So just to remind you, so that this is actually the table of r-squared values, the fit table for the previous hierarchical regression that we ran, just for comparison. So the model that had identification first, job satisfaction, age, and sex second, and annual salary third. Okay, just for comparison. Now this is the equivalent table for the analysis that we've just run. Okay, so now this is the one that has annual salary first, job satisfaction, age, and sex second, and identification last in the final block. Okay, and the model comparisons table. Okay, so now this is telling us, this comparison between model 2 and model 3 is telling us that adding identification last rather than first, it explains an additional 7.9% of the variance in commitment, and that is significantly different from 0. So with all the other things in the model already, identification on top of those explains a further 7.9% of the variance in commitment. Okay. So that's hierarchical regression analysis, and again, I think one of the key considerations is in doing it, it can be very powerful and a very useful tool for inferring things about the importance of individual predictors. But again, just to re-emphasize, that question of when and where individual predictors or sets of predictors go in such an analysis is a thing that is related to your research question and what you want to know, rather than something inherent to the variables themselves. So just to close off on hierarchical multiple regression, I want to highlight just one thing. These are the coefficient tables from the first hierarchical regression that we ran. So this is the one, the model that just had identification. Then the second one, in which we'd added that block with job satisfaction, age, and sex. And finally, the one that included annual salary. Now, a key thing I want to point out here is that although it remains significant throughout, the coefficient of identification gets smaller as additional predictors are added to the model. So it actually falls from about 0.62 right down to about 0.38 when you're also adjusting for these other predictors. So why is that? Why might the role of one predictor change when you add other predictors to the model? And the basic answer is that in regression, unlike say in an experiment that you might analyze using analysis of variance, in regression, especially with measured predictors, your predictors, your IVs, can also be correlated with one another. And that has a number of important implications for how you think about the meaning of a given set of results. So let's think about that in slightly more sort of abstract and conceptual terms. The implications of predictors or IVs being correlated with one another. So let's say we're interested in explaining variance in a dependent variable. So this is just a variance in a DV represented as a circle. Okay. And we have two predictors. So we've got predictor A and we've got predictor B. Now in this case, predictors A and B are not correlated with one another. Okay, they do not overlap. So variable A and variable B don't overlap with one another. They don't share variance. And in this case, they each explain unique variance in the DV. Okay, so this is variable A explaining or overlapping this amount of variance, and variable B explaining or overlapping this amount of variance. Okay, so we enter A and B as predictors in a regression, and they may both come out as significant predictors of our DV. Now let's look at a slightly different case here. So here we have variables A and B being correlated with one another. They actually share variance with one another. They overlap. So in such a situation, you may enter a simple regression where A predicts the DV, okay, and it does appear that A by itself significantly predicts variance in the DV. It turns out to be a significant predictor. But what might happen then is if we then add B, variable B, in a second block, A becomes non-significant, okay, and B is a significant predictor. Now the reason for that is that this bit of variance that A appeared to be explaining is not actually uniquely attributable to A, okay, because it is also shared with variable B. Okay, so that correlation between A and B now means that this bit of the variance that previously was attributable to A is no longer uniquely attributable to A. Instead, the only bit of the variance in the DV that can be uniquely attributable to either of the predictors is this bit here. Okay, and that is attributable uniquely to variable B. So in this case, we might have a final model in which B significantly predicts the DV, but A does not. Okay. Let's take a final example where variables A and B, our two predictors, are actually quite substantially correlated with one another. They're highly overlapping. Okay. So in such a case, if we enter both of them, so let's say we enter each of them individually into separate simple linear regression analyses. Okay, both of them, each individually, share quite a bit of overlapping variance with the DV. So this is variable A's overlap and this is variable B's overlap. So individually, they may be highly significant predictors of the DV. However, we enter them both together and it turns out, because they're so highly correlated with one another, that very little of that shared variance in the DV can be uniquely attributed to one or other predictor. Okay, only these tiny little portions up here and down here. Okay, so it is possible to have a case in which you have two predictors, each of which individually by themselves predicts the DV, but when you enter them together, their correlation with one another means that neither of them turn out to be significant or unique predictors of the DV. Okay, so overall message here is when you are thinking about the implications or what the inferences that you make for a multiple regression analysis or whatever it might be, it's important to think about not just the associations of predictors with the DV, but also the associations of the predictors with one another. Okay, and for that reason, it's often now seen as best practice if you're presenting any sort of multivariate analysis, say a multiple regression or a mediation, as we'll see in next week's session. It's also good practice to report a table of the simple bivariate correlations between all of these variables, so we can see the basic associations between them, and then also that gives some context for the actual analyses that you've run. Okay. All right, time for a little break. When we come back in part 2 of this week's session and part 3 of our regression refresher overall, I'll revisit categorical predictors in regression and then move on to cross-lagged regression. Okay, see you shortly.